Hello students. Over the past 2 to 3 weeks, nearly 4 weeks, what we were looking at in module 1 was what do we mean by an ISA, what all information does it give, and then we were looking at how the compiler and assembler would be built for a given ISA. Right, in the as part of ISA, the addressing modes were there and the instruction encoding was given and the number of instructions was given, the type of instructions, and also the registers that the ISA expects that the hardware should provide, etc. Now in this and the next module we are going to look at more towards the microarchitectural aspects for a given ISA. What do we mean by that is just like we understood some of the aspects on what the compiler and assembler would do for an ISA. Now we will look at the layers below the ISA, right? Basically the hardware for a given ISA. Okay, before I dive into the actual concept, a quick points on basics. So what typically the modern day processors are built with are transistors, and more specifically the metal oxide semiconductor field effect transistor, MOSFET in short. So it has primarily 3 terminals: source terminal, drain terminal, and gate terminal. And there are primarily 2 types of MOSFETs, NMOS and PMOS. And if we build a circuit with both the NMOS and PMOS transistors, then we typically call that as CMOS, which is complementary MOS. Right, and here is a picture of PMOS transistor. It has what's called as N well and P substrates on top of that, right? And there is a gate oxide which is made with the metal. That's why it's called metal oxide semiconductor field effect transistor. So it's called field effect because when we give a sufficient voltage to the gate terminal, which is here, these 2 terminals, there will be a current flow or there will not be a current flow. The field between these 2 would be affected by the voltage given to the gate, right? So if we want to take an example of NMOS, for example, based on the voltage given at the gate, the connection between the source and drain will be determined, and accordingly we interpret that the transistor is in some state. So if you give a very high voltage to the gate, the source and drain terminals are connected. It means that there will be electron flow between those 2, and we say that the transistor is on. If the gate voltage is low, then the source and drain are not connected, so there is no current flow between them, and we say that the transistor is in off state. This is for NMOS, and for PMOS it's exactly the opposite. What does that mean? When we give a high voltage to the gate, the source and drain will be disconnected and that particular transistor is said to be in off state. And when we give a low voltage to the gate of PMOS, the source and drain are connected and it's said to be in on state, right? And this is the only level of abstraction that I expect you to have. No, I don't want you guys to go any more deeper on how it's actually working and all that. This is what we can stop it. We are going to move more towards microarchitecture rather than device level. Now when we say technology scaling, the one we saw was Moore's law, which was saying that that the number of transistors in a given space right, would double every 18 to 24 months. Basically, the transistors would shrink in size. And accordingly, we say or we refer each technology as a technology node followed by uh, a number which is in nanometer now, like 7 nanometer, 10 nanometer, 14 nanometer, etc. Now, what does that refer to is the gate length, the distance between the source and drain terminals. Now, when we say from one technology to other technology, the transistors are shrinking, primarily it's the gate length that is shrinking, right? Now, from this basic NMOS and PMOS, we can go ahead and build some circuits that we are more aware of, right? If we are looking at a CMOS inverter, it would look something like this. There will be two levels of voltage given, VDD and VSS, and there is an input A and output Q, right? The transistor on the top is the PMOS and the bottom is NMOS. If you look at them closely, there is a bubble for the gate terminal at PMOS, right? Just to distinguish the PMOS and NMOS operation. Now, how does this work as an inverter? For example, when we give a very high voltage to A representing the bit 1, then the PMOS transistor will be off. So the source and drain terminals are disconnected. So VDD is disconnected to Q, and the NMOS transistor will be on. It means that Q will be connected to VSS. So which is which is typically low, and that will be interpreted as a 0. Now the exactly reverse operation would happen when we want to drive a low voltage at A, saying that it's a 0. Right? In that case, the PMOS will be on, NMOS will be off, and VDD would be connected to Q. It means that I'm giving a 0 at input and I get a 1 at the output. That's what the inverter would typically do, right? In the same way, we can build a NAND gate using the PMOS and NMOS transistors. So here we have two NMOS transistors which are connected in series and two PMOS transistors which are connected in parallel. Again, you can extend the same operation like if A and B both are high, right? What happens is both the NMOS transistors are on, so C would be connected ideally to the ground, right? Which would be 0. Then the other combinations you can cross check. So if we want to look at the CMOS NOR gate, it's exactly in the reverse combination. It means that the PMOS are connected in series and NMOS are connected in parallel. Now, if you want to see how it would work, let's say both A and B are 0. So again, the NMOS transistors would be on and they would be connected to the ground would be connecting to C, right? Basically, it would be 0 at the output. So even if one of them is on, then the ground terminal is effectively connected to C, right? So you can extend these and build much bigger circuits, which you are already have gone through in the digital logic. Now, can you realize an AND or XOR and other gates using these basic NAND, NOR, and NOT gates? Yes, right? And we can extend further and build more logic blocks like the decoders and encoders and multiplexers, demultiplexers, then arithmetic circuits like the half adder, full adder, and extend them further to create a ripple carry adder and even further a better one, which is carry look ahead adder, right? And we can build the multiplication and division circuits. If you are not already aware of the Booth's multiplication, do have a look at it. It's a very intuitive algorithm that speeds up the multiplication a lot, right? And then we can extend it further, extend the basic gates further to build the flip-flops, SR or JK or D flip-flop, etc. Basically, many of them are cross-coupled gates, right? And if you want to refresh your memory, I would suggest you to go through some of the contents of chapter 6 in Carl Hamescher's computer organization book, the 5th edition, or you can also go through the appendix A of the textbook that we are currently referring by Patterson and Hennessy. So this is the only abstraction I expect, and you can imagine all these relevant circuits, the adder, multiplier, shifters, etc., are available to us in the ALU. ALU you would have already designed in your digital logic, right? Moving on, excuse me, a quick recap of what we touched upon in module 1 is we have 5 different components of the computer: input, output, memory, data path, and control path, right? And then when we were specifically focusing on the memory and the CPU, or the processor, you can say, we were looking at this particular diagram where the memory and the processor are connected by a processor memory interface, and within the processor we have the control circuitry which would drive all the other modules in the processor, and we have the ALU where all the logic blocks are sitting, and then we have a few additional registers like the PC and IR, followed by some other general purpose registers, right? Now the number of general purpose registers and the logic in the ALU is completely determined by the ISA, right? And also the granularity that by which the granularity required to interact with the memory, and how we interact with the memory, basically the data transfer instructions, etc., are all determined by the ISA, right? Now the input output module, we are going to look at it at the later half of the course, but right now we are going to dive into the processor module. We are looking at the stored program computers primarily, which means that both the code and data of a program are sitting in the memory. So it means that for each program there will be a text segment and there will be a data segment. Along with that, you would remember the snapshot of the memory, that there is a stack and a heap, etc., right? To identify the addresses of instructions, we have the program counter, and PC typically points to the address of the next instruction that we need to execute. And instruction register, IR in short, will be holding the machine instruction of the one which are currently we are currently executing, right? A small point on the notation that we are going to follow: if we place PC or any registers in square brackets, we would refer to the contents of that PC or register. Now if we place that in two double brackets, what we want to refer is the contents of the location pointed by the PC, or the contents of the location given by that particular register. Okay, so here to quickly correlate, the contents of IR would be the contents of the location pointed by PC. Okay, we are going to use this notation. Now in this module, we are going to look at how the processor works, and basically when we say what the processor does is it executes instructions, right? Let's look at one particular instruction and see how it goes about it. The very first thing that the processor would do is fetch the contents from the memory location pointed by PC and place them in the instruction register, right? It means that we go to the text segment of the program which is lying in the memory, using the PC as its address. We are going to tell the memory, get me the data in this particular, or get me the contents in this particular location. when the memory responds, we place that in the instruction register. And we also increment the PC to the next instruction because we wanted to point to the next instruction that we want to execute. So if we are taking a 32-bit instruction width, then the next instruction would typically be 4 bytes later. For moving on, the contents of the instruction register are now closely looked at, and it would tell us to perform one or more of the actions that we are listing now. Either it would tell us to read the contents of a given memory location and load them into a register. This would be our typical load instruction, right? Or it would the contents in IR can say that read data from one or more registers and perform some ALU operation on it. So this would be our arithmetic instructions. And the result of this operation can would be eventually put in some other register, right, which would be the destination register. Or the contents in IR can tell us that get the address using a register and an offset and place the data of some other register in this particular location of the memory. So this would be a store instruction, right? The instruction register would be telling us one of these or few others like the control instructions also. We are going to look at that. Now, how does the hardware go about this third step is what the entire discussion would be about in this module, right? Now, let's go a little finer. Before that, a definition, the steps 1 and 2 would be typically called as instruction fetch phase, and the steps in 3 are called instruction execution phase, right? In a CISC type ISA, because the instruction can now span multiple words, right? The steps 1 and 2 might be repeated multiple times. In a RISC style ISA, we would give an address and get a word of data. But in CISC, we also need to figure out how many words we need to fetch. So that would be known in the very first fetch that we would do. Okay. Now let's look at each of the instructions and try to differentiate each of the steps in how we go about executing those instructions, right? Let's start with load instructions. Let's take the example of load double x5, 16 x6. The very first step would be fetching this instruction from the memory using its PC, and immediately we increment the PC. PC equals to PC plus 4 typically, and then the machine code of this instruction would be in the IR. So we go about decoding this instruction. Now, how do we decode this instruction? We follow exactly the reverse procedure that the assembler does. What does the assembler do? It picks an assembly instruction and checks for the opcode, function 3, function 7, immediate, RS1, RS2, RD, etc. all these fields, and it creates a 32-bit machine word, right? Machine code. So we do the exactly opposite thing. We take this 32-bit machine code and then look at the opcode, function 3, function 7, etc. And then we would know which type of instruction it is. Based on that, we are going to pick the other fields, whether it might be immediate field or RS1, RS2, and RD, etc. Okay. So here, when the hardware would decode this particular instruction, it would realize that it needs to read the register X6. It means that contents of register X6 will be brought into the ALU, and the immediate value, which is 16 here, will be added to it. The resultant is what's called as effective address, right? This effective address will be sent to the memory module, saying that get me 32 bits of data, or here it would be load double, right? So we tell it to reply us with 64 bits of data. The memory would respond, and after we receive the response from the memory, we place that data into register X5. Okay, these are the steps to execute a load instruction. The first two are we can group them into 5 different stages, explicit stages. The first step or stage is called fetch stage. The second and third steps are grouped as decode stage. The third step, where we are calculating the effective address, is the execute stage. The fourth step, where we are talking to the memory, is the memory access stage. And the fifth step, where we eventually update the destination register, is the register update state. Let's do the same exercise for an ALU instruction. Let's consider the simple add x5, x6 and x7 instruction. By the way, here we are considering the two source registers and one destination register. Instead, even if we take any immediate instruction like ADDI, where we have one source and one destination with an immediate value, the steps will be more or less same. The very first thing is common. Using the PC, we go and fetch this instruction and place it in instruction register, and also we increment the PC. Now, the second step is where we decode this instruction. At that point, we recognize that yes, it is an add operation that we need to perform, and we'll also identify the RS1, RS2 and RD. Here RS1, RS2 are X5 and X6. X6 and X7. So those two registers will be read from the register file. The values we get from X6 and X7 will be consumed by the ALU, and the operation we need to perform is simple addition. It performs that, and the resultant would be placed in the destination register, which is X5. Now here we have only 4 steps. Earlier we had 5 steps. To make it uniform, if you remember the regularity principle, it will make the hardware simpler. So we say that typically in 4th stage, where we're supposed to access the memory for the ALU instruction, we don't need, so we do not do any action here. Means the hardware will not change its state. And as a 5th step, we are going to write the result of the ALU operation to the destination register. So again, we have the fetch stage, decode stage, execute stage. The 4th stage, we are not doing anything, but it would typically be part of memory access. And the 5th one is the register update stage. Let's do the same for the store instruction. Here it's store double X6, 16 and X5. Both X6 and X5 are the source registers, and 16 is the immediate field, right? So the first step is again same. Using the PC of this instruction, we get it from the memory and we place it in the instruction register. We also increment the PC. In the second step, we are going to look at each of its individual fields. That's when we realize that it would be a store double operation. Accordingly, we pick the RS1, RS2 and immediate fields. At that point, we will know that RS1 is X5, RS2 is X6, and we get the data from that data of those registers from the register file. And in the third step, we are going to compute the effective address. Basically, it would be the immediate value plus the contents of X5. This again, like I mentioned in the load instructions execution steps, it's called the effective address calculation. This address will be communicated to the memory, but here it would be said that in this address, write the value that we got from X6, right? This would be the store operation. And typically there is no 5th step because we are not updating any destination register here. But for uniformity, we are going to make it as a fifth stage with no action. So again, we have the fetch stage, decode stage, execute stage where we are computing the effective address, and in the memory access stage we are doing exactly opposite what we did in the load instructions. Here we are saying to the memory, go to this particular address and write the value that I am giving you. In the load instruction it would be exactly opposite. We would say go to this particular memory location and get the value that's already in that location, right? And as a fifth step, there is no register update here. So if we look at all these individual steps, we would need to build the hardware to carry out each of these steps, right? So let's look at what all hardware is needed for this. The very first one would be the processor memory interface with the internal registers MAR and MDR, right? Following that, we also need what's called as instruction address generator, IAG in short. It also has PC within itself. We need the hardware to store the instruction register, right? Along with that, we have the hardware of the registers itself, which is a register file, and we need the ALU to perform all the operations also, right? To guide all these modules, we need the control circuitry. So the control circuitry forms the control path of uh, the instruction execution, right? And all the other modules form the data path. In this module, we are going to dive into each of them in detail, right? Uh, with that, I will pause this lecture. Thank you.